Hi there. I want to talk about correlation and what it is and what it is not, and what key properties we need to know about correlation coefficients. So, which of the following is false? All but one of these are true. So, correlation measures the strength of linear association between two numerical variables. That's what a correlation is, and that's what it's for. So let's pull up an example. Let's say we're looking at the correlation between height and nose. Two quantitative variables, numerical variables. So here is what the scatter plot would look like. Okay. And we can see that as one variable increases, the other increases, and there's a correlation between the two, which means that the Pearson's R would not be close to 0. If I go ahead and compute the regression line, so that's add trend line, and I'll just add a linear regression line to that. And while we're there, I'll display the equation on the chart and the R. So we notice that the R squared is 0.2184. The actual correlation between those two variables is going to be, let's zoom in a little bit. Okay. Equals correl, gives me the correlation between height, comma, and then I select the array of data for nose. And the correlation is 0.46. It's a pretty big correlation. The R squared is 0.214. And anyway, this is a positive linear relationship. If we had a negative linear relationship, it would have these scatterplot dots going down. And I'll demonstrate that. So here is a scatterplot of data with a correlation of nothing. And it just looks like a bunch of random dots on the page. As I change the correlation coefficient, I can increase it. What we have here is a correlation of 0.41, a higher correlation 0.6, and keep going up. So we have 0.88, and it keeps going up until every point is on a perfect line at R equals 1. If the correlation is 1, then all the dots in the scatter plot would be on a perfect line going up. Now go back down to 0, and as we approach negative, we see here I've got a large negative correlation. That means as x increases, y decreases. And furthermore, I can keep going down to -1. So correlations range from 1 to -1. And they're only good at detecting linear relationships. So here's a perfect positive, here's 0, or 0-ish, and here's a perfect negative, and everything in between is how we get our correlation coefficient. It characterizes the strength and direction of association between two quantitative variables. Meanwhile, if I'm looking at a quadratic relationship, such as this one here, I'm going to make this bigger, bring it to the front. Okay, what we have here is two variables that are related, but not in a linear way. I'll move this to a new sheet so it's more clear. Related, but not in a linear way. There's a clear pattern between temperature and aggression. People get meaner as it gets hotter, but then it levels off and actually goes down after a while. So the linear relationship between these two variables is 0. And I can show that by adding a trend line. So click anywhere on the dots, right click, add trend line. And a linear relationship here has a correlation, a low R squared, so 0.09. There is an obvious pattern in this data set, but it's not a strong linear pattern. It goes down, but only just a little bit. And the correlation between those two variables is, let's look at it, equals correl, okay, between temperature and aggression, -0.3. So it's actually a modest correlation, but when we look at the pattern, it's a very strong and obvious quadratic curvilinear pattern. Correlation isn't good at detecting that. It's going to think there's pretty much no relationship there in terms of linear patterns. So correlation is good for detecting linear and only for detecting linear relationships. Next question, or next option, if the correlation between two variables is close to 0.01, then there's a very weak linear relationship to them. And that is the situation. Here is an example of what that would look like. I'm going to create a simulation with that correlation. Simple correlation, and I'll make it 0.01, as close as I can conveniently get it. There's basically nothing going on there. They're basically unrelated. Okay. Next option. Correlation coefficient and slope always have the same sign, either positive or negative, and that's true. So let's look at the relationship between regression and correlation. Demos, regression. I have, here I've got r equals a very positive 1 here, and if I add some more points to it, I've got a strong correlation, and the regression slope, you can see, is positive in all of these situations. And if I make it smaller, that decreases the r, and eventually if I make it small enough, I can make it be negative. It's tricky, but possible, considering what I started with. So here I've got a negative 0.5 correlation, and the slope becomes negative as well at that point. So if the correlation is negative, that means the slope of a regression line would also be negative. That's the line that predicts the relationship between the two variables. So I'm going to actually remove some of these other outlying points to make it more obvious that there's a pattern here. Okay, but what is not true, as you can see, the slope is not always equal to the regression correlation. A coefficient is not always equal to the slope. And in general, they won't be the same. So let's demonstrate that. The last option here on our list is if the correlation coefficient is 1, then the slope must be 1 as well. That's not true. Correlation being 1 means that the variables are perfectly related, that if I know one, I can predict the other. That doesn't mean that they are the same scale. So what I've done here is taken our nose length, these are just measures of noses, and I've said take that, multiply it times 6, and subtract 50. Okay, so that's just nothing more than a variable that has been, I've added a constant and multiplied it times a constant. So it has not changed at all. So the correlation is perfect. R is equal to 1. And yet the slope of the regression line, as we can see, is 6. And that's because I multiplied the variable times 6. So slope of the regression line will always have the same sign as the correlation coefficient, but it will not always be the same number. And in fact, generally it is not. So the only option here that is false is if the correlation coefficient is 1, then the slope must be 1 as well. All the other statements are true by definition of correlation.